Alright, it's on. Go to the bathroom while I wait, and then I'll go.
Lost inside this moment as your memories fall away. All you've got are pieces of the dream you couldn't save. The story's all but over, and this ending's got you trapped. Left with no tomorrow and no way of turning back.
But love is always on our side. We'll make it through tonight. Somehow we will. And oh, we'll keep the spark alive. As time keeps rushing on, each breath's a chance to try. Though no one ever said just how our story ends, we will find another waiting to begin. And if we leave this life, we keep the love we find, flowing on forever like rivers in the sky. Feel your pulse inside you. It's a sign that nothing's lost. There's a way to break through. Just make sure you count the cost. You are not your ending. You are not where you began. So leave it all behind you. Put your life into his hand.
'Cause love is always on my side. It all could change tonight. Somehow it could. The end may be a dark divide, but if the rush should come, you're gonna be alright.
Though no one ever said just how our story ends, we will find another waiting to begin. And if we leave this life, we keep the love we find, flowing on forever like rivers in the sky.
Though no one ever said just how our story ends, we will find another waiting to begin. Another clues will find that we are so alive, flowing on forever like rivers in the sky.
Alright, here we go. So, for tonight, we are just going to look at the practice test. So you guys saw this yesterday, or today in class. If you need a copy of it, and you have access, if you're one of my students, you have access to it, it's on my e-class page. You can just go under Content, then Unit 8, and it's under there as Common Assessment Review. So it's roughly 40 questions, so I'm just going to go through. I'm going to go through how to think through each question and talk through each subject as we get to it, and then we'll call it a night, and everyone will take the test tomorrow, get an A, and we'll all be happy. Woohoo. Okay, so that's what we're going to do. I noticed that we have a Star Trek emoji. That's pretty cool. I'm waiting for the lightsaber emojis. When do those come out? Alright, so here we go. Looking at our, let's see, I want this size. Number 1, here we go, here we start. Which of the sets of coefficients correctly demonstrate the law of conservation of matter? Now, there's a couple things in here. Okay, a couple things we need to pay attention to. Number 1, the word coefficients. We need to know what that word really entails, okay? So remember, coefficients are different than subscripts, okay? So if we have H2O over here, this 2 is a subscript, where this 2 would be a coefficient. And this one is a subscript. They are two different things. Remember, subscript denotates how many atoms of the element there are, and the coefficient denotates how many molecules of the entire compound there are. Okay, so they mean two different things. Okay, so as we go through, which of the sets of the coefficients correctly demonstrates the law of conservation of matter? Remember, the law of conservation of matter says matter cannot be created nor destroyed. All of the atoms on the reactant side of the equation must be the same as on the product side. So however many sodiums you start with, how many oxygen atoms you start with, you must have the same on the right side. You must have the same exact number of sodium and the same exact number of oxygen. So real quick, let's do our atom inventory. We have our sodium, we have our oxygen. Let's count on the left hand side. You take your coefficient, which is currently blank, times your subscript, which is blank. When they're blank, that's 1, so 1 times 1 gives us 1. 1 times 2 gives us 2 oxygens. Now on the right hand side, we have one compound. Okay, 2 elements coming together to form one compound. This is a synthesis reaction. We have 2 atoms of sodium and 1 atom of oxygen. Now right away we can see that these don't equal. 1 does not equal 2, 2 does not equal 1, so we do need to make some changes. Okay, so real quick, this is O2, we'll just leave that as is. Let's fix this. We can put a 2 right here, fix that, that changes this to 2, and it changes this to 2 times 2 gives us 4. And then all we have to do, 2, 2, we're good. All we have to do is fix this 1, and we can quickly do that by putting a 4 right here. So now we're balanced. 4, this is blank. Remember, whenever it's blank, that's a 1. That is a terrible one. That is a 1. So 4, 1, 2. We look down here. 4, 1, 2. Boom. There's our answer. We're moving on. Okay. So that's a simple balancing equation question. The same number of atoms on the left-hand side as on the right-hand side. That's not the same thing. It's not the same number of compounds, right? This is 1, 2 compounds on this side, and this side only has 1. It's synthesis. The 2 come together to make 1. We're looking at the number of atoms on each side. That's what we care about. Okay, that's where the law of conservation of mass comes into play. All right. Question 2, 4Fe plus 3O2 yields, remember this arrow is read as yields, yields 2Fe2O3. Cool. This is also synthesis. 1 plus 1, okay, so we have these 2 different elements. They combine to form one compound, and that is synthesis, 2 things coming together to make one thing. How many grams of oxygen are needed to react with 350 grams of iron to produce 500 grams of 2Fe2O3? Now, we don't really need this 2 right there. That's just telling us that's, copy paste, someone messed up. Okay? But really we're just talking about this this compound. Now this goes right hand in hand with our equation up here. We know, due to the law of conservation of matter, that the reactants must equal the products. You cannot create mass, and you can't destroy mass. So, the mass of the reactants must equal the mass of the products. Now, for our reactants, we have Fe, and we have O2. For our products, that's the left-hand side. What we start with, those are our reactants. What we produce on the right-hand side is our products. Our products is Fe2O3. So, real quick, the mass of iron plus the mass of our oxygen must give us the mass of our iron oxide. It's just the law of conservation of matter. If you start out with certain amounts of mass and then you end with certain amounts of mass, then you will satisfy the law of conservation of matter. Okay, so over here it says 350 grams of iron. So this one is equal to 350 grams. This one is our unknown. This one is equal to 500 grams. So it's going to be our unknown plus 350 will give us 500. This is the mass of our products. Our mass of reactants must equal the mass of products, so we can just quickly do our unknown is equal to 500 minus 350, which gives us 150 grams. Okay, if we look over, here it is, 150 grams. Okay, there we go, we're done. That's number 2. First page, done. Let's go to page 2. Alright, question number 3. Oh, look. See, when it's not printed black and white, you get these nice little colors. Alright, first thing you always do, very first thing you do, if you are given a test question that has some sort of image attached to it, the very first thing you do, don't even read the question, very first thing that you do is you look at the image, you figure out what it's trying to tell you, and then you can go through and actually answer the question based on that. Okay, so here we have color-coded. We have our blue plus our red, or blue bonded to our red, plus our yellow bonded to our green, and we got some arrows. Okay, this C has an arrow going up and over to the A has an arrow going over to the C. Then we have our yields arrow. Then we have our orange bonded with our red, and our blue A bonded with the green D. So right away I can tell this is a double replacement reaction. We have our first compound, our second compound. There are 4 different types of elements here. The A and the C switch over. Okay, and then they swap partners, and they result in our new compounds of the the second cation with the first anion, and the first cation with the second anion. Okay, so cool. Which of the following correctly describes the reaction shown in the above diagram? Okay, here's the thing. Because I looked over this image already, I already know the answer. I don't even have to read it. It says describes the reaction. I already said it's double replacement. We saw that already. We have switching of partners. We have our cations switching over and bonding with the other anion. I know for a fact it's double replacement. So the very first thing I'm going to do, find the one that says double replacement. The reaction is single replacement. No. Goodbye. The reaction is single replacement. No. Goodbye. I'm not even reading the rest of it. Don't waste your time. The reaction is a double replacement. Good. The reaction is a double replacement. Good. So it has to be C or D. Okay? So you answer the first part of the answer, and then you can move on to the second part. The second part is dealing with cations. Cations are A and C. Anions are B and D. Now, it's the same. They just switch. This is A and C. This is A and D. So they switch different ones. So right away, we know that one of these cations has to be A. Okay? We know that A has to be a cation. Okay? And we know due to ionic bonding, cations are like cats in that they're positive. Yeah, it's stupid, but you're going to remember it. Okay? Let's move my camera down real quick. It's stupid, but you remember it. So, when you are looking at what's going on, use that stupid thing to remember. Cations are positive. You list your positive ones first. NaCl, right? This goes down to Na plus. This goes over to Cl minus. This is your cation, which means this must be your anion. So, your cation is first, your anion is second, okay? A is first, good. C, is C first? CD, CB, yes it is, that's the correct answer. Whereas D is listed second, therefore it's an anion. The ones listed first, A and C, are our cations. The ones listed second, B and D, are our anions. Okay, so this is a simple vocabulary question. Can you classify the reaction, which we did right away, and then do you remember the vocabulary of what cations and anions are, which, luckily for us, there's an easy way to remember it. Cations are positive. There you go. Ready to move on. Question 4. Select the two equations which demonstrate the law of conservation of mass. Now remember, law of conservation of matter, law of conservation of mass are the exact same thing. You can use them interchangeably. It means matter or mass cannot be created or destroyed. We are given a bunch of equations. Therefore, it's just looking to see which ones are balanced. And it says the two equations. So we're going to have two answers. Okay, real quick. Do an atom inventory. That's all you got to do for this. Is it balanced? Yes or no? Okay, so we have Mg, we have S. 1 Mg on this side, 1 Mg on this side. 1 S on this side, 2 S's on this side. So real quick, I'll write it out. Mg, S. Do real quick. 1, 1, 1, 2. We know right away this is not one of the answers. It is not balanced. Okay, then we have C and O. On this side we have 1, we have 2. On this side we have 2 and 1. That is not one of the answers. Now, luckily for us, it says two equations which demonstrate we've already eliminated A and B, so process of elimination says C and D must be the correct answers. But real quick, let's do them. Cu, which is copper, and then O, which is oxygen, and we have 4 on the left, 2 oxygen on the left, and on the right we have 2 times 2 gives us 4, and we have 2 times 1 gives us 2, so yes, that is one of the answers. And then the last one, we have H and O. This is 4 on this side, 2 coefficient times 2 subscript, and then 2 oxygen, 1 coefficient times 2 subscript. And then we have water on the right, 2 times 2 gives us 4, and 2 times 1 gives us 2. So we can see that both C and D are balanced, and since they're balanced, they are demonstrating the law of conservation of mass, and they're good to go. But again, we eliminated the first two right away. We know pretty sure that they aren't there, so we know it had to be C and D. We just proved it to ourselves over here. Okay? Alright, question 5. Look at the following equation. Now, you're probably smart enough, you probably know this already, but anytime they give you an equation, okay, and look, they give you an equation, and they give you this thing right here. Oh, they give you a blank line in front of every compound. That is a key indicator that this equation is not balanced. If they give you blanks there, you are going to have to fill in the blanks. You will have to balance the equation. Okay? In order to follow the law of conservation of mass, this equation must have which set of coefficients in order from left to right. Okay, so left to right. So this is going to be your first one, second one, third one, fourth one. And if you look down here, you can see first one, second one, third one, fourth one. So it's like they go in line. Okay, so real quick, let's just balance it. NaCl, Ca. So this is, oh, I'm still in yellow. NaCl plus calcium fluoride will yield sodium fluoride and calcium chloride. Now they switch partners. This is double replacement. NaCl, Ca, and F. Okay, so now we can write in our things. My camera's just getting in the way today. We'll put it in the middle. Sure. Real quick, Na, 1 on this side, Cl, 1 on this side, Ca, 1, F2. On the right, 1, Cl has 2, calcium has 1, fluorine has 1. So the things I need to fix are the chlorine and the fluorine. Okay, so on this side, I'm going to write in a 2. That will change this to 2 and change this to 2. Now I got to fix this side. I'll put a 2 here, changes this to 2, and then changes my Cl to 2, 2, 2, 2, 2, 1, 1, 2, 2. I am good. So my coefficients are 2, 1, 2, 1. Look, 2, 1, 3, 1, 2, 2, 2, 2, 2, 1, 2, 1, boom. That one matches what I know is the balance. That one is my answer. Okay, so simple, balance the equation. Again, a giant hint. Whenever they give you a line in front where the coefficient is supposed to go, you're going to have to balance it. Question 6. Sophia performs an experiment in which she adds 10.0 grams of zinc metal to 25.0 grams of bromine. She claims the mass will be conserved during the reaction. Which of the following best supports her claim? So she's made a claim, now she needs some evidence. Okay, so here's 4 pieces of evidence. Let's see which one is the best for her claim. The mass of the final product will be equal to the mass of the zinc metal. So what is she doing? She's doing zinc, which is Zn, plus bromine, Br, except it's Br2 because it is diatomic, and it's going to make products. Okay, and gives us products. Doesn't say what the products are, it's just going to give us some products. Okay, so it's saying that the mass of the products will equal the mass of zinc. Okay, but remember, the mass of the reactants must equal the mass of the product. So if the mass of the products only equals one reactant, you're not satisfying the law of conservation of matter, so therefore your mass isn't being conserved, therefore we don't want that. Okay, that's bad. The mass of the final product will be equal to the difference between the two masses, 15 grams. So she has 10 grams here and 25 grams here. So our products, theoretically, 10 plus 25 should be 35 grams. This is not what the mass of the final product would actually be. We know it's going to be 35, so that's out. Okay, mass of the final product will be equal to 25. We know that's not right. We know it's 35, and the mass of the final product will be equal to 35. There we go. Okay. Now, a lot of the times you can answer these questions without even reading the answers, okay? And that's what I advocate. Do that. Go out and answer the question, then come back and check your answers, because we said 35, and lo and behold, here's the answer choice with 35 in it, so we're good to go. Which of the products in this reaction? Now, chemical equation, we have 2 sides to it. We have the reactants, and we have the products. And give me 1 second. Okay, sorry about that. We have our reactants, and then we have our yield 0, and then we have our products. Okay, so left side reactants, right side products. Okay, and this is where the chemical change occurs. And we're good to go. Okay, so the left sides are reactants, right sides are products. Now, we can have multiple reactants. We can have 1, 2, 3, 4 reactants almost. We can have multiple products. We can have 1, 2, 3, 4, 5 products even. Okay, and so when you look at the equation given to us, we are given 1 plus 1, so, and then a yield 0. So this side is one side. Then we have our arrow, and then this side is the other side. Okay, so it says, which one are the products? Well, the products are whatever we produce. So these things are combining. They go through a chemical reaction, a chemical change, and they will produce our new things. And our new things are called our products. So this side, the whole right side, is called your products. Okay, so anything on the right is considered a product. So in this case, we have carbon dioxide and water. So find carbon dioxide and water. Here it is. Carbon dioxide and water. That's our products. Anything on the right-hand side of the equation is the products. Okay, so that one's, do you know how to read an equation? Pretty easy. All right, now we get to the fun stuff. This is the stuff I really love, when they give you models, okay? Because the models don't require any math, and they don't require anything beyond just looking at the image and doing a little bit of thinking. Not even a lot, just a little bit of thought process will tell us what's going on. So here we go. We have one giant gray ball. We have a small speckled ball. We have a small speckled ball. They are touching. They are obviously bonded. Okay, we then have our yields arrow, then we have the gray ball by itself, and we have the diatomic speckled balls over here. Cool! One thing, yields arrow, 2 products. One thing, breaking apart into 2 different products. That is obviously decomposition. Boom, done, move on. We got it. That's it. Moving on. Question 9. This is an unbalanced equation representing a chemical reaction. Which of the following is the balanced equation? Okay, so let's balance it. Literally, that's all they're saying. Balance the equation. We have, I'm going to write down here. Okay, we have fluorine plus potassium chloride. We have fluorine plus potassium chloride. Fluorine is diatomic. Will yield, let's look up, Kf plus Cl2. Now, what type of equation is this? We have fluorine reacting with KCl, and then all of a sudden we have Kf, and Cl is all by itself. So one thing comes in, kicks out the other, and moves on. This is single replacement. So let's balance it real quick. We have fluorine, we have potassium, we have chlorine, FKCl. Okay, coefficient 1 times our subscript 2, so that gives us 2. Coefficient 1 times 1 gives us 1, and 1 Cl. On the right-hand side, F. Find F, 1, 1, cool. K, also 1, Cl, A, 2. So we can tell that this is unbalanced right away. They don't match up. 2, 1, bad. 1, 1, fine. 1, 2, bad. Okay, so we got 2 bads here, not going to work out. So real quick, let's balance it. Okay, I need to fix my F first, so I'll just put a 2 here. Changes this to 2, and then all I have to do, this potassium will then change to 2 as well. So I have to fix 2, 2, that's fine. Now I have to fix potassium and chlorine. Look at this, they're bonded together. One single coefficient will make my life happy. So, since this is nothing, that's a 1, 2, 2, and this is also a 1. So let's go back up. Let's find F2 plus 2 KCl. So F2 plus KCl, nope. F2 plus KCl2, nope. F2 plus 2KCl, F2 plus 2KCl, good. Gives us 2KF plus Cl2. 2KF plus Cl2, boom. Balance the equation. Pat yourself on the back. Move on. Have a good day. Alright, now here's the one that's a little bit scary. And why it's a little bit scary? Well, look at this. Question 10 starts here and gives you a small little couple paragraphs, or not a paragraph, a couple sentences. Then it gives you a giant image. Then it gives you more. Then it gives you another image. Then it gives you more. And then it starts giving you your answers. And look, the answers aren't even on the same page. Okay, this is a little scary. This requires a little bit of reading. Okay. As we know, most of the reading that happens on sign tests is kind of useless. Okay, all that really matters is we know what's going on with the images. This is just giving us some sort of scenario that we may or may not care about. So let's see what we do care about and what we don't. Students in Mrs. L's class are designing experiments using baking soda and vinegar. We've done this. We've done this. Okay. Baking and soda together. Remember, we put it, made gas. Cool. Group 1 places 25 grams of vinegar in a flask. Look, here it is. Vinegar, 25 grams. 5 grams of baking soda in a balloon, 5 grams in here, and look, oh my god, 25 plus 5 grams is 30. They stretch the balloon over the mouth, combine it, the flask is weighed throughout the experiment, and 30 grams, 30 grams, 30 grams. Now the baking soda went into the vinegar, some gas went up into the balloon, the mass never changed. Okay, this sounds about right. This is kind of what we've done already. Group 2 does the same thing, but they don't use a balloon. Haha, dummies! Instead, Group 2 scoops the same amount of baking soda into the open flask of vinegar. They put it in. It starts at 25. They're not weighing the baking soda at this point. They add it in. Now they have the baking soda and the vinegar. And then all of a sudden, we have to figure out what's happening. There's a question mark here. How would the final mass experiment most likely compare? Alright, so they added in the baking soda. They got 30 grams. Now we have this guy right here. As we all know, it's making gas. Gas is coming out. Group 1 literally filled up a balloon. Remember, gas is matter. Matter has mass. We are losing mass. Not only is gas going up, matter is going out, and matter has mass! Exclamation point. So therefore, not only is matter going up, but mass is going out. So if mass is going out, we start with 30, we're losing mass to the atmosphere, it's going to be lower than 30. Alright, let's read the things. The final mass in Group 2's experiment will be greater. Well, 30, losing mass is greater, unless you're losing negative mass, which is not a real thing. If it was, diets would be awesome. That's wrong. B, the final mass in Group 2's experiment will be less, will be less than the final mass in Group 1's experiment because gas is allowed to escape, decreasing the final mass. That sure sounds like what we've already described. I'm going to put that as my answer, but I'm going to read the other two just in case. Final mass in Group 2's experiment will be the same. Nope. Final mass will be greater. Nope. Okay, well, listen. Even if you didn't know the because, there's only one that says it's going to be less. We know it's going to be less. We watched it happen. So, therefore, that's our answer. Cool beans. Ready to go? Question 11. Look at the following chemical equation. Zn plus 2HCl yields ZnCl2 plus H2. Is this chemical equation balanced? Okay, real quick. Yes, yes, no, no. So real quick, let's balance it. Zn plus 2HCl yields ZnCl2 plus H2. So they've already tried to balance it. There's already a 2 here. So real quick, all we have to do is take our atom inventory. Okay. So Zn on 1, 2, and 2. On this side it's 1, Cl2, H2. Look, 1, 1, 2, 2, 2, 2. It's balanced. So we can come back over here. We can look at yes, yes, no, no. So we know it's balanced, so we get rid of C and D. Yes, because the number of the reactants is equal to the number of products. Yes, because the number of atoms of reactants is equal to the number of atoms of products. Okay, this could be a little bit confusing. Okay, a little bit confusing. When you are looking at this explanation, it says number of reactants. Now, if you're not thinking closely, you might just think the number of reactants might be these guys right here. Okay, this is the reactant side. We put some numbers. There we go. It's not. when they say number of reactants, they mean how many reactants they actually are. 1, 2. Okay? And then it says number of products. So 1, 2. Now, this seems right. 2 reactants, 2 products. But we know, guys, we know synthesis reactions. Decomposition reactions. You go from 2 reactants to 1 product. 1 reactant to 2 products. We know that that's not the case. We know that there are plenty of examples where we don't have the same number of reactants and the same number of products. Instead, what we do have is we have this sucker right here where we write out the actual numbers of our atoms of the reactants and the number of our atoms of our products. So that has to be the right answer. Now, if you are not thinking, if you're going too fast, if you're not making sure you actually know what you're answering, A looks very, very good. It does. It looks like the right answer. But it's not. And you have to make sure that you go through and you have to make sure you know what you're answering. Okay? Because these answer choices are so easy to trip up on. And then you missed a question that you knew the right answer for, and you missed the points because you didn't just think through it. Okay? You can't do that. You can't miss easy points. Question 12. Balanced chemical equation below shows the reaction between nitrogen N2 and hydrogen H2 to form ammonia NH3. And look, it's balanced. It told us. Okay, so we know it's balanced. If 10 grams of nitrogen reacts with hydrogen to form 12 grams of ammonia, how many grams? Look, guys, mass of reactants is equal to the mass of products. We know this. We know that to be the case. The mass of reactants must equal the mass of products. So if it was 10 grams of nitrogen, so it's going to be N2 plus H2 yields NH3. We know that this was 10 grams, and we know unknown will give us 12 grams. Make sure I have my numbers right. Yeah, 10 grams plus the unknown gives us 12 grams. Okay, what's 10 plus x is equal to 12? What's x? Well, obviously it's 12 minus 10, which would give us 2 grams of hydrogen. Okay, there we go. Easy peasy lemon squeezy. Moving on. Okay, the graph below shows the effective temperature on the volume of a gas. All right, now we're in gas laws. Okay, conservation of mass. Taking a back seat for this question. We're in gas laws now. Alright, let's look at our graph. Through the power of technology, I get to zoom in on it. You can just hold the paper closer to your face. Effective temperature on the volume of gas. We have volume on our y-axis, temperature on our x. Now remember, in science, we usually put the independent variable on the x-axis. The independent variable says the variable that I, as the science experimenter, as the scientist, I am controlling something. Okay? I am controlling something in this experiment. I am changing it. That is my independent variable. Okay? That is what I control. And in the case, the easiest thing to normally control is temperature. So usually, the scientist will control the temperature. Okay? So, as we see, x-axis, this is our independent variable. Now, this is like dominoes. Okay? I am pushing over the first domino. Now, there might be another domino behind that domino that when I push the first one will fall into the second one, and that second one will change position. Either it'll get knocked back a little, it might wobble a little, it might fall over completely, it might be too far away that the first one doesn't even affect it. But any change that happens to that second domino was not done by me, it was done by the first domino. I might have pushed the first domino, but the first domino then impacted the second domino. What we call the second domino is what's impacted by what we change. That is our dependent variable. It depends on the independent one. The reason the dependent one changes is because it got forced to change by the independent variable. And that goes on our y-axis. So that is our volume. Our volume is our dependent variable. So as the scientist, we are changing the temperature, and we are observing what happens to the volume. So we're controlling the temperature, usually on a hot plate. We're controlling the temperature. We're reading what changes to the volume, and then we know what our temperature was at because we controlled it, and we know what the volume was at because we measured it, and we take that and we put it into a graph. And now, looking at this graph, we can say some things. This graph is a straight line. It's linear. Okay, we know that. We know that this graph has a positive slope. It is going up. Okay, graph going up. Going up, positive slope. Now we know, because it has a positive slope, as you get higher with your temperature, as your x-axis goes up from 0 to 10 to 20 to 30 to all the way up to 60, well 50, all the way up to 50, we can see that as the temperature rises, we have a positive slope, meaning our volume is also rising. We started at 0 and 60. We then went to 10 and 62. We then went to 20 and 65. We then went to 30 and 67. We then went to 40 and 69. Okay? Every time the temperature is increased, we can see, based on the data we collected, based on this graph, that our volume is also increasing. This means there is a direct relationship between our two variables. Now, what are our two variables? Okay, direct relationship between the independent and the dependent. I can't spell. Dependent. Okay, we know we have a direct relationship, independent and dependent. Now, what was our independent? Was our temperature. What was our dependent? Our volume. So, let's look at our answer choices. What generalization can be made between the temperature and the volume of the gas? As the temperature of a gas decreases, the volume will increase. Now, this is not what we just described. We described the temperature getting higher and the volume also getting higher. As you go across the x-axis, you go up the y. Okay, positive slope, direct relationship. If one gets higher, the other gets higher. So that is not our answer choice. That is not what we want. B, as the temperature decreases, the volume stays the same. If it stayed the same, it'd be a straight line all the way across, and that's not what's on the graph, okay? So that's wrong. C, as the temperature of gas increases, its volume also increases. Or D, as the temperature increases, volume stays the same. We know it's not that one, and we know that as one got bigger, so did the other. This has to be our answer. Okay? The relationship between volume and temperature is one that is direct. If pressure remains the same, an increase in temperature allows the particles of gas to absorb that thermal energy, the increase of temperature. Thermal energy coming in gets converted into kinetic energy. Those gas particles start moving around. Okay, they're going. As they move faster, they're going to hit the containers more. Okay, so they're moving faster, they're going to hit the sides of the container more. If the pressure stays the same, that means every time they hit the container, it moves the container out. As your container moves out, it's getting bigger. The volume is getting bigger. Okay, so as your temperature increases, the gas particles start moving faster. The reason they start moving faster is the thermal energy gets converted to their kinetic. We know temperature is the average kinetic energy of the particles. So as the average kinetic energy goes up, the speed of the particles go up, the motion of the particles go up. They start moving faster. They're going to hit the wall more. Every time they hit the wall will be pushed out. Okay, so your volume will expand. This is all, remember, this is assuming the pressure is constant. Okay, so this is the interconnectedness between the idea of what's happening to the particles to how we can measure that based on an experiment, and then the generalizations we can get from our knowledge of the particles and our looking at the data, and we can come up with the rules of what they're following. And that's exactly what we're doing here. As the temperature increases, the volume is also going to increase. This is Charles' law. Okay, took us as humanity a very long time to figure this out. Okay, but we did, and now it's easy, so we can move on. Question 14. Under what circumstance might a gas decrease in volume when heated? Okay, so this is looking at the gas laws. So for our gas laws, remember, we can memorize all three. We can do PV equals PV, we can do V over T equals V over T, we can do P over T equals P over T, or we can just remember the combined gas law, which is just P1 times V1 over T1 is equal to P2 times V2 over T2. Okay? So, our combined gas law. So, we know our relationships between pressure, temperature, and volume. We know that pressure and volume have inverse relationships. Pressure and temperature have direct, and volume and temperature have direct. Okay? So, we want the gas to decrease while we're heating, we want the gas volume to decrease while the temperature is increasing, okay? Volume and temperature have direct relationships. So if the pressure is constant, if you increase the temperature, you'll increase the volume. We just saw that, okay? So that means if a volume is going to decrease while the temperature is increasing, that the pressure is obviously not going to remain constant, okay? The pressure is coming into play. And so we know inverse relationship, that the pressure increases, the volume decreases. So find the one where it says the pressure is increasing, because if the pressure increases at a faster rate than the temperature increases, well, then the pressure will win, the volume will end up actually decreasing due to the combined gas law when you add them all together. So which one is the pressure going up? Gas is held at constant temperature and pressure. No, that's constant. Gas remains under uniform temperature. Uniform is just another word for constant, and it's not even talking about pressure, and it already says it's heated, so we know temperature is going up. Gas is placed under increasing pressure, and the gas undergoes a decrease in pressure. Okay, so again, here we go. PV equals PV, Boyle's law. Okay, we know that if pressure goes up, volume must go down. Okay, so we want the increasing pressure. Boom. Okay, so this one requires you to know all three of your relationships and be able to apply them with the combined gas law. Okay, that's what it's looking for. Question 15. Will you get the formula during the test? No, you will not. Okay, all you really need is your PTV. Just write out PTV on your popsicle stick, and then you can know the relationships that way. Otherwise, you just have to know it. Okay. All right, the pressure of a gas inside a closed, rigid container. Code words. Code words. They are speaking in code. Closed. We know that that is a closed system. What does a closed system mean? It means that you cannot have matter leaving or going in. Rigid. Rigid means it's not moving. Okay? So if it's a closed system and it's not moving, these are code words for volume is constant. Okay, code words. The pressure of a gas inside a constant volume container will increase when the gas temperature increases. The pressure of the gas increases because. Okay, so this is looking at pressure and temperature. So we have our P, we have our T, we have our V. Okay, if we had it on our popsicle stick, right, we have the closed rigid means our volume is constant, so you'd put your hand, look at this, put your finger over the volume and then push up on your temperature. What happens to your pressure? It will also increase. Now, think about what's happening to the particles. If you know what's happening to the particles, you'll never miss a question like this. As the gas temperature increases, now we're in a closed box. The box is rigid. It cannot change size. Okay, so as your temperature increases, the particles now have more kinetic energy. That thermal energy is converted into kinetic energy. The average kinetic energy is your temperature. The particles are going to start moving faster. As they move faster, they're going to close the distance to the wall faster, meaning they'll hit the wall more often. Well, if the wall can't move, then you just have it hitting the wall, hitting the wall, hitting the wall way more than it was. And we know that every collision that it hits against the wall applies a little bit of force. Okay? And that force from all the gas particles hitting the wall is what we call our pressure. So more collisions means more force, more pressure. Okay, so as your temperature increases, so does your pressure. Density of the gas increases. Now, density. Whoa, we're coming back to this one. Rate of collisions of gas molecules with the surface increases. That's what we just described. Okay, container expands. It said it's rigid. Can't expand if you're rigid. Okay, gas molecules bond together to form more massive molecules. We have not talked about that once ever. That's gone. So now, look here. Rate of collisions of gas molecules with the surface increases. We talked about that. As it goes faster, it's going to hit the container more often. Boom, more collisions. That's our answer. Now, this one, this little guy right here, density. Okay, our density. We know that density is equal to mass over volume. Okay, so the things that can change density, mass or volume. You can change mass by getting rid of particles or adding more particles. That's the only two ways. Okay, conservation of mass. You can either add more particles to it or you can allow it to take away. But we saw it's a closed system. So since it's a closed system, there's no movement of matter. There is no your mass stays constant. It's closed. Okay, mass cannot go in or go out. So that's constant. So the only thing that can affect density is the volume. Okay, and it says it's rigid. It's rigid. Volume can't change. So the mass is constant, the volume is constant, the density is constant. That is not the answer. Okay, you got to think through what each variable means, what each thing is happening with the particles and with the container they're in. Okay, and that will always lead you to the right answer. All right, page 8 of 19. Good Lord. Good Lord, we're almost halfway there. Alright, question 16. The gas inside a sealed container is heated. Uh-oh, code word. Code word. Sealed. Sealed means closed. Closed means closed system, meaning the gas cannot escape. Okay, a sealed cylinder is heated. Which of the following does not increase as the gas is heated? Okay, the average number of gas molecules hitting the cylinder walls per second. This is a lot of words. This is gas hitting cylinder. This means pressure. Okay, gas hitting cylinder, pressure. Average kinetic energy. Average kinetic energy. This means temperature. This is a vocabulary question. Do you know your vocabulary? Do you know what all these words mean? This is pressure. This is temperature. The average speed. Average speed. Well, that's speed. How fast are the molecules moving? Speed. The average distance between the gas molecules. Okay, distance. So this is how far away they are. Okay, now, if we're adding heat, okay, heat is thermal energy, right? As we add thermal energy, it's going to be converted to the gas molecules. Okay, it will be converted to kinetic energy. Okay, energy conservations, we know this. Okay, so we are adding thermal energy, which is adding kinetic energy. If we're adding kinetic energy, then the average kinetic energy of the gas molecules is gonna go up. Boom! I found my answer. Woo! We're done. Moving on. Now I'm going to talk through all of them. Okay, average number of gas molecules. That's pressure. As you heat up the... Oh my gosh, I made a mistake. See, this is what I'm telling you. You get going too fast. You don't realize exactly what you're looking at. You don't realize exactly what you're saying. You're going to miss a question you know the answer to. It happens to everyone. Just happened to me. It will happen to you. Okay? Here's what the issue. Does not increase. I answered as one that does increase. This one does not increase. Okay, so you better read the question, otherwise you're going to make the same mistake I did. Okay, which of the following does not increase? If thermal energy is being converted to kinetic energy, we know the average kinetic energy, that means the temperature is going up. This cannot be the right answer. Okay, so the average number of gas molecules hitting the cylinder walls per second. Now, this is a sealed cylinder. We know that it's not. It's a cylinder. It's probably made out of metal. It's not going to expand. We know our volume is constant. Okay, and if our volume is constant, then we know that as the temperature goes up, the pressure will also go up. They are directly related, so that is not the case. Okay, C, the average speed of the gas molecules. As your temperature goes up, you have more kinetic energy. Kinetic energy is the energy of movement. More movement energy means more movement. They're moving, their movement is going around, so if there's more of it, that means they're going around even more, so their speed is increasing. It's not that one. Whereas the average distance will not increase because that's how far away, which is directly related to the volume. You need volume, you need more volume to be able to get further away, okay? You can have all the energy in the world you want, but if you're stuck in a closet with someone, you're still not going to get farther away from them unless you actually are in the entire house, okay? You have more room to actually run around. So the only one that does not increase is D, and if you didn't read the question, like I didn't read the question, you would have missed that question, okay? Don't miss easy questions. 17. The picture below shows a gas at standard conditions in a container with a movable piston. This is a lot of words. Okay, container. Here we are, piston. And we see that this is the piston. Okay, it's right here. So this is like our syringe. Our piston can go up or our piston can go down. What does that mean? If our piston can go up, we'd have a bigger tube, and if it went down, it'd have a smaller tube. So that means movable piston means our volume changes. Okay, so it's all about interpreting the setup. We know that with our syringe, our plunger and our syringe, okay, it went up and down. We changed our volume. That's what's going on here. Our volume changes. According to Charles' law, dun, da, 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 Charles' law tells me that V1 over T1 is equal to V2 over T2. Thanks, Charles. What will happen to the piston when the gas is heated? As we heat up, okay, so we have V1, T1. If T2 is bigger, so V1 over T1 is equal to question mark over T2. T2 is now bigger. See, it's bigger. Get it? Bigger. What's going to happen to our V? Okay, so as T2 gets bigger, we know that this is directly proportional. If these are the same number, right, because this is a fraction, it's this divided by this. It's going to be this divided by this. It's got to be equal. We know that V2 must also be bigger. So which one is the larger volume? To get a larger volume, our piston needs to go up. So the piston will move up because the gas particles get larger. This is right. That's not. Gas particles are staying the same size. The more temperature means they just move faster. So that's wrong. B, there's no change because the heat will not affect the system. Get out of here. C, the piston will move up because the gas particles move faster and get further apart. Sounds good to me. So far, so good. Piston will move down. Nope. Goodbye. So answer is C. Okay, as you heat it up, the gas particles start moving faster. As they move faster, they would hit the piston and push it up, okay, allowing the gas particles to spread apart. Page 9. Question 18. A cylinder of gas particles is shown below. Here's our cylinder. Look, it's got a piston again. Okay, cylinder is fitted with a movable piston. Yep, see, you look at the image before you read the question, you're already 2 steps ahead. Which of the following would result in an increase in pressure of the gas below? So our pressure is going up. Now we know that when pressure goes up, volume must go down or temperature must go up. Okay, so whatever one. It's either pressure up leads to volume down, or pressure up leads to temperature up. Okay, those are the 2 relationships. So, increasing the volume, nope. Removing some of the gas, no, it's a closed system. Decreasing the volume, as pressure goes up, volume goes down, yep, that's right. Or decreasing the pressure. How can you, like it says increase in pressure, then it says decrease the pressure. Like, come on. Get out of here. C. Question 19. A picture of a turtle killer is shown below. Alright, this is, it says, I love murdering sea life. See, he's unabashed. He is unabashed. He has no cares, and look, he's got a happy face. He's so happy about the turtles that he's going to kill. So happy. Alright. If the temperature of the balloon were to decrease suddenly, temperature going down. That's either going to lead to volume going down, or it's going to lead to pressure going down. Okay? We know that they're directly related with both of those. How would the balloon change? Its mass would increase. Well, temperature is not related to mass in any way, shape, or form. That's gone. Its mass would decrease. Again, not related to mass. Its volume would increase. As temperature goes down, volume goes down. So it has to be volume would decrease. Okay? Cecilia, don't get mad at me that I'm deleting your spam. I don't care about your emojis. Alright, 20, let's zoom in a bit. The illustration below shows a hot air balloon. Look how good of an illustration this is. That's much better than I normally give you on tests. The pilot can change the altitude of the hot air balloon, but altitude means how high or going up or down, by changing the temperature of the gas inside the balloon, hence why it's called a hot air balloon. When the gas is heated, the balloon rises. Which of the following best explains the phenomenon? We learned this last semester, guys. Come on. As you heat something up, as you add heat, we have convection currents, right? The convection currents occur because when you heat something up, you increase the temperature, okay? And when you increase the temperature, the particles start moving faster. As they start moving faster, they have more kinetic energy to move further away from each other. As they move further away from each other, our temperature goes up, which leads to our volume increasing. Now, as the volume increases, look at this, density, mass over volume. As our volume increases, okay, that means our density, which is the mathematical formula of mass divided by volume, our density is going to get smaller. As you get less density, your density will go down, and the less density you have will go up. Less dense things rise. Okay? More dense things sink. So if you increase the air, you increase the temperature, you increase the volume of the gas inside the balloon. The gas inside of the balloon all of a sudden becomes less dense. As it's less dense, it starts to rise. According to the gas around it, it's less dense, so it's going to start to rise. You now have a balloon that will go up into the air. Woohoo! Flying. Heating the gas reduces its pressure. No. Heating the gas decreases its density. Oh, yeah. There we go. B. Heating the gas decreases molecular motion. Actually, heating the gas adds molecular motion, so that's wrong. Heating the gas reduces the frequency of the gas molecules' collisions. With each other? I mean, yeah, it doesn't reduce it. It increases it, so that's wrong. It's got to be B. All about the density. Mass over volume. 21. Which of the following occurs when a rigid container of gas is heated? Rigid. Code word. Code word. Code word. Rigid. That means volume stays the same. Volume is constant. Cool. The pressure inside the container increases. Okay, so volume is constant. We know our P, T, V, our popsicle stick here. Okay, we know volume's constant, and then it's heated. So we put our finger on the V, we push up on our T. What's going to happen to our pressure? It will also go up. Okay, pressure inside increases. Boom. Pressure decreases. No. Pressure stays the same. Nope. Pressure changes the composition of the gas. No, it's definitely not going to change what the gas is made out of. Okay, now remember what's happening to the particles. As it heats up, they have more kinetic energy. They move faster. Moving faster means more collisions with the wall. Since the wall, it's rigid, it will not move. More collisions means a higher force, means a higher pressure. Okay, because pressure is the force from the collisions. Okay, so as your temperature goes up, your pressure also goes up. All right, 22, and the answer is all graphs. So, if the answer is all graphs, here's what you do. Don't look at the graphs. Don't do it. You're just going to confuse yourself. Don't look at the graphs. Draw your own, and then match yours to one of the answer choices. Boom. Save some time. Assuming pressure is held constant. Okay, so pressure is held constant. Which of the following shows how volume changes with temperature? So if pressure is constant, we know that as temperature goes up, our volume will also go up. So if we change our temperature, so we'd have T on our x-axis, we have V on our y. As our temperature gets higher, volume gets higher, so as it gets higher, positive slope. And we're good. Now we just find the one that looks like this, and look, boom, A. It's right there. Okay, look, as your temperature gets higher here, your volume gets lower. As your temperature gets higher here, okay, your volume does get a little bit higher. And as your temperature gets lower here, your volume also gets lower. Okay, but let's look. This one is the only one that's linear. Okay, and we know that they're directly related, so we know that it's going to be a linear relationship. A. Good to go. Alright. Can you guys chill? If you're not here to go over the quiz, you don't have to be here. You can leave. You don't have to spam my chat and force me to read it and time you guys out. 23. The diagram below shows gas inside a sealed container before and after force is applied to the container's movable piston. So, a lot of keywords here. Sealed. Closed system. Make sure we know how to read these. Forces applied to the movable piston. This means volume changes. Okay, volume changes. The temperature inside remains the same after the force is applied. So we have our force going down. Our temperature actually stays the same. Okay, and we can see 25 to 25. Now, what changed? Okay, so temperature was constant. We pushed down the volume. So the volume went down. We pushed down the piston, so it had all this space. Now it has all this space. Okay, so our volume went down. Applying the force to the position results in a compression of the gas particles. They were all out here. Now they're compressed and looking like this. And an increase in pressure. So we know pressure went up. Okay? Which of the following statements best describes the change in the gas particles? If our temperature is constant, that means the kinetic energy of the gas particles increases. Well, temperature is average kinetic energy. So if it's constant, then the kinetic energy is the same. Okay, so that's gone. Kinetic energy decreases. No, we just said it's the same, so that's gone. Now, the velocity, that's speed, remember, okay, with which the gas particles hit the container increases. So are they hitting the container harder? Are they running faster into the wall? That's what it's saying. And the only reason that particles move faster is if they have more kinetic energy. If they have more kinetic energy, that means their temperature is higher. Our temperature was constant. So they're moving at the exact same velocity. But what is happening is they have a smaller volume. They're hitting the container more often, resulting in an increase in pressure. So the frequency, how often it happens, increases. But the speed doesn't increase, just how often it happens. And since it happens more often, we label that as pressure increasing. Okay, so our temperature was constant, our volume went down, so our pressure went up. That is Boyle's law. A party shop delivers helium-filled balloons to homes and businesses. They're terrible, they should be out of business. The owners realize from experience that on a hot summer day, they should inflate the balloons only 3/4 full. And on cold winter days, they can fully inflate the balloons. Which is the best hypothesis to explain it? Okay, so hot means that they cannot put all the helium in it. Cold means they can put more helium into it. So the helium gas is more active in the winter season. I don't know what that means. I'm going to eliminate it. I don't know what it means. Air outside the balloon leaks into the balloons. So the air is going into the balloons as if it's an open system. Okay. That's a weird hypothesis. As the temperature increases, the helium in the balloon expands. Outside air pressure in the summer is less than indoor air pressure. Okay, well, we've never really talked about air pressure. This is the only one that talks about a gas law. As your temperature goes up, it results in your volume going up. They're directly related. We know that already. As a hot day means more temperature, means that the helium will expand, forcing the balloon to be more inflated because the helium is taking up more room. Whereas on a cold day, the temperature goes down once you leave your warm shop. Okay, that means your volume is also going to go down. So you need to overfill the balloons so when they shrink outside, they still look filled up. Okay, so there you go. No, you will not get the gas law formulas. That's like the third time I've answered that question. All from you, too. Maybe when you ask a question, you should listen for the answer. Two boxes, A and B, both contain the same number of nitrogen gas molecules. Okay, so same number of molecules. The gas molecules in box A have twice the average speed of the molecules in box B. Which of the following best describes the nitrogen in box A? If they have twice the average speed, how do gas particles have more speed? Well, speed is directly related to kinetic energy. I don't know why I just wrote P. It's related to our kinetic energy. Okay, so box A has more kinetic energy. That's all we need. Nitrogen in box A has a greater mass. Nope, they have the same number. Same number of molecules means the same mass. Nitrogen in box A has a greater density. Well, they have the same number of molecules, and it doesn't say anything about the sizes. So and density doesn't really deal with speed, so that's out. C, the nitrogen gas in box A has a greater temperature. Nitrogen gas in box A has a greater specific gravity. Yeah. If you see something that has literally nothing to do with what we're talking about, don't even give it the time of day. Just eliminate it and move on. If A has more kinetic energy, we know average kinetic energy is temperature. This is the only one talking about a greater temperature. Has to be the right answer. Don't even waste time on D. The illustration below represents the expansion of gas in a cylinder of an engine. The piston, which we know is this thing, moves as the gas volume changes. So here we only have half a liter, here we have 1 liter. So as your volume goes up, or as more gas is there, the piston gets pushed up. Okay. What could have been done to the gas in the cylinder to bring about the change in volume? Okay, so if the volume increases, there are things that control that. That would be the temperature increasing, the pressure decreasing, or no, well, this is just the gas laws right here. So let's see. Half the molecules were released. If you have half the molecules, you don't really need the same space. So you're not going to take up twice the amount of space. So that's gone. Temperature was doubled. Okay, temperature goes up, volume goes up. Yes. The amount of heat in the gas was reduced. Temperature goes down, volume would go down. Nope. Pressure on the pistons was reduced. Pressure goes down, volume goes up. Yep. E, the temperature was reduced. Nope, temperature's got to go up for volume to go up. Pressure on the piston was doubled. That would be pressure going up, which would mean the volume would go down. That's wrong. So the answers are B and D. They're the only ones that match our gas laws. Okay, so when you get something, all you got to do is write out what you know and then base everything true or false on what you know. Literally, true-false question. True. This is false, this is true. This is false, this is true. False, false. Ready to move on. When a scuba diver is deep underwater and exhales, air bubbles form and rise to the surface of the water. Choose the correct term from each drop-down box. Okay, so we got terms. About what happens to the air bubbles as they rise to the surface. The number of molecules in the bubbles and the diameter of the bubbles. Okay, and the number of molecules. So choose the correct term to complete the statement about what happens to the air bubbles as they rise. Okay, so will the number of molecules increase? No, the bubble stays the same no matter what. So it's going to remain the same. But as they go up, remember, the further down means the higher pressure. So as they go up, your pressure is actually going to go down. Pressure going down means your volume will go up. So your diameter, which deals with how big the bubble is actually going to increase. So remember, the deeper underwater you are, the more pressure. And then as you come up the water, you're having less and less pressure. And so lower pressure will result in a higher volume. There you go. So the number of molecules stays the same. It's the same bubble throughout the whole way, and yet the bubble will end up being larger at the top, at the surface, than it will be at the bottom. What about 26? It says, what could have been done to cause it to change? These are the only two things that could have been done. We know to cause it to change, for the volume to increase, which is the change we observe and the change they tell us. The only two things that are listed that could have caused it to change are the temperature going up or the pressure going down. And these are the only two answer choices that talk about the temperature going up or the pressure going down. Okay, so that's why these two are correct. It's true, false. Which one matches your gas laws? That's all it's asking. Question 28. Some manufacturers place rubber plugs in the bottom of pressurized aerosol cans to prevent structural failure if the cans are exposed to excessive heat. The normal pressure inside the can is 2 atmospheres at 27 degrees Celsius. When the temperature of the gas in the can is increased to 250 degrees, that's a big increase, 27 to 250, the pressure can reach 3.5 atmosphere and the plug will pop out. Which of the following graphs best shows the relationship of pressure to the temperature inside the can? Okay, so here we go. Draw your own graph. We know temperature is changing. We know that's what's causing it to change. Okay, which means pressure must be our y-axis. As our temperature goes up, we can see the temperature went up, and therefore the pressure went up. Okay, so as temperature goes up, the pressure goes up, until the plug pops out. Now, what happens when the plug pops out? So you have this can, and you got a plug in it. Okay, like a cork. It's basically a cork. So if you have a can with a cork in it, then at a certain pressure, you have all of these air particles hitting the sides of the cans, and as it goes up, they're getting more and more energetic, faster, faster moving, more kinetic energy, higher temperature. They're hitting more and more. They're going to hit that plug more often. If they hit the plug with enough force, enough pressure, unfortunately, that's kind of like when you shake up a can and you screw the top shoots off. Okay, that's exactly what's going to happen. Okay, temperature. Oh, why does temperature go on the x? Because that's our independent variable. That's what's changing. Okay, we're increasing. It says the temperature of the gas is increased. That's what we changed. Okay, we changed it by putting it in a hot car. Well, if your car's 250 degrees Celsius, you're dead. But the idea is still the same. We put it in the hot oven. Okay, and we got it all the way up to 250 degrees Celsius. Okay, that is what we changed. And because we changed it, it goes on the x-axis. Okay, and we can also see that it's on the x-axis every single time. Okay, now pressure will go up as the temperature goes up until you have enough to push out that cork. Now, when you shoot that cork, your pressure, now it's an open system. Now that you have an open system, you have gas molecules escaping from the can. If you have gas molecules escaping, that means there are less molecules to hit the sides of the can. And since there's less collisions with the side of the can, our pressure is going to drop until it hits a nice little area where it's finally equal. The pressure inside is equal to the pressure outside, and then it will just be a straight line. Okay, so we have our pressure going up with our temperature, we have a drop, and then it's nice and equal. Now, this one goes down, drops, and then is equal. Okay, that's not right. This one goes up, and then all of a sudden goes even higher. That's not what we looked at. This one looks exactly like what we just drew. This one has a little curve here. Okay, that little curve is bothersome, because that means that it wasn't really a direct relationship. Okay, as we went up, there was not necessarily the same direct relationship. Pressure kind of stayed the same, and then it went. So that's a little worrisome. This one looks exactly like what we drew. A direct relationship. The cork pops, the pressure drops so until it's equal to the pressure outside, and then it stays the same. So D is our answer. Okay. This one is a little bit of an advanced problem, so I'm going to pause real quick. If you have questions about it, let me know. Okay, I'm moving on. Almost there. 29. A student noticed that an inflated balloon gets larger when it's warmed by a lamp. Okay, which statement best describes? So, warmed by a lamp. Warmed. That means our temperature is going up, and we saw it got larger, so our volume also went up. Okay, we're doing a lot of Charles' Law today. The mass of the balloon increases. No, the balloon doesn't stay. It stays the same. Okay. Oh, I didn't read the question. Dumb me. Which statement best describes the mass of the balloon as a result of the change. As our temperature went up, our volume went up. Did our mass even change? No! Why would the mass change? Okay, so mass of the balloon increases, gone. Mass of the balloon stays the same. Mass of the balloon stays the same. Okay, so we're down to these two. Because the gas inside the balloon still has the same mass after it warms up. Because warming decreases the mass enough to cancel out the effect of increasing... that sounds like a made-up answer. If the mass is the same, 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 it's 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 the conservation of mass, it cannot change unless it's an open system, and the mass can leave and be somewhere else, okay, but this is not, it's a balloon, this is a closed system, the mass stays the same, conservation of mass, easy peasy, moving on. The reaction of element X, squares equals X, and Y, circles equals Y, is represented in the following diagram. Here's the diagram. Which equation properly describes the reaction between X and Y? Okay, so here we go. Alright, and look, it's balanced. Oh my god, it's balanced. Now, let's look here. Let's start with this one. This one looks a little easier. Okay, so we have our products, and we have our reactants, right? We have our products, we have our reactants. On the reactant side, we have 2 circles. That's Y, right? So we have, and they're not bonded. They're 2 completely different Y's. So we definitely have 2Y. Okay, and then we have 1 square bonded with 2 Y's. So that's going to be X, and then it's going to be Y, and it had 2 of them. 2. And how many are there? There's 1, 2, 3. So that gets a nice big old 3 in front of it. Now on this side we have 1, 2, 3. So we have 3x plus 1, 2, 3, 4, 5, 6, 7, 8y. Okay, let's look. 3x plus 8y is equal to x3, y8. Nope, that's not what we wrote. 3x plus 6y. Nope, not what we wrote. X plus 2y. Nope, not what we wrote. 3x plus 8y gives us 3xy2 plus 2y. Look at us go. Now, this is where it's very, very important not to look at the answer choices before you come up with an answer. If you started looking at these answer choices, you are going to confuse the ever-loving crap out of yourself. Do not do it. Okay, you will start looking for these answers in the diagram, and you're going to convince yourself you see it when it's just not there. Okay, if you just ignore them, write out your own interpretation of the diagram, and then see if it matches any of them, then you're not going to confuse yourself by trying to make something fit that is obviously not going to fit. You can convince yourself of anything during a test. Don't do it. Write out your own answer, then compare it to the answers given to you. Now, if we wrote out our own answer and it wasn't one of these answers, then you were back to square one. Okay, then you might have to start looking and try to get rid of some and move on from there. But if you write out your first one and boom, there it is, you circle it, you move on, you don't waste time on it, and you don't confuse yourself out of the correct answer that you already knew if you just spent 10 seconds to think about it. Okay? You're going to spend far more time trying to match those wrong answers to the diagram. You're just going to result in wasted time, wasted effort, a confused brain, feeling like you don't know anything, circling an answer just as a guess because you want to move on, and you're going to end up with it getting wrong. Instead, take 10 seconds. Try to think about it yourself. 10 to 30 seconds. Write it out yourself, and then match that to one of the answer choices, and I promise you, if you spend enough time and you think about it and you actually write what you see, you're gonna find the right answer there. It's gonna match what you did, because if you are not concerned about the wrong answers they gave you, you're gonna come up with the right one. And once you come up with the right one, it's just a matter of circling the right answer and moving on. Okay, so again, I'm going to go over one more time how I found the right answer. Okay, and it took about 30 seconds of thought process. Okay, and then we were able to move on. Okay, look at this. So we have, let's color this in. So this is, we'll call this green, and we'll call this blue. Okay, so let's look. I always start on the side that has less. It's just easier for me to count. It's not that it has less drawings, it's just they're grouped up, so it's easier for me to do it. Okay, so X is the squares, right? So I'm just going to go in and 1, 2, 3. So I need a total of 3 X's. And Y is the circles, so I have 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, and then 1 by itself, 1 by itself. Okay, and then we can do that over here as well. You can just color them in. Now obviously I have tools that allow me to color them. Okay, you might not have that, but that's okay. Alright, so when we look here, I can see that I have an X bonded with 2 Y's. Okay, so I have X and Y. They're bonded together, and there's 2 Y's, so I put a subscript of 2. And then I can see that these are Y by themselves, right? So I have Y by itself. I have X and Y2, 1 X, 2 Y's. Okay, and then I just count to put my coefficients, 1, 2. So I put a 2 in front of that one. And then I have 1, 2, 3, so I put a coefficient of 3. That tells me there are 3 molecules of XY2. Okay, now on this side, nothing is bonded together. So I have Y by itself, and I have X by itself. Okay, so now I just count. I have 1, 2, 3 X's by itself, and I have 8 Y's by itself. So now all I have to do is take my reactants, write them down. Take my my products and write them down. Okay, and that's exactly what I did right here. I had 3X plus 8Y, and it's going to yield 3XY2 plus 2Y. Okay, and that, lo and behold, is answer choice D. Okay, so 30 seconds to think about it will save you a lot of headache and save you a lot of confusion, and you'll be able to just move on. Okay, you'll get the right answer, you'll feel good about yourself, you'll realize that none of this is as hard as it actually looks, and you'll be able to not only get a good grade, but you'll actually understand why the answer is correct. Okay, getting the right answer is good and all, but if you get a right answer because you guessed on it, well, you can't really replicate that, right? Unless you just guess right every single time. In that case, please buy me a lottery ticket. Okay? Figure below represents a reaction. So here we go. We have S. Big thing is a sulfur atom. Yeah, we can see that. The black one is oxygen. And then we have oxygen with 2 small ones is a hydrogen. Okay, so we have 2 things coming together to form one thing. 1, 2, reacts to form just 1. So 2 things coming together to form one thing, that's synthesis. Okay. Decomposition is one thing breaking apart. Single replacement is one thing replacing something in a compound. Double replacement is partner swap. But when we have 2 things coming together to form one thing, well, that's synthesis. And it really doesn't matter what any of the atoms are. Doesn't matter. All that matters is that 2 things are forming one thing. It's synthesis. Okay. Home stretch. Home stretch, number 32. Zoom in one more time. 5 chemical reactions are listed in the table below. 1, 2, 3, 4, 5. Identify any synthesis reactions. Okay, so you can quickly get overrun by what these look like. Okay, quickly get overrun by them. Okay, that's not the point. It says which ones are synthesis. And we know synthesis is more than one thing forming one thing. So we have one thing breaking apart into 2. Nope, that's decomp. We have CaOH2 plus 2HCl gives us CaCl2 plus 2H2O. That's Ca switching partners, the hydrogen switching, this is double. Double replacement. Now, do you have to go through and actually identify every single one of these? No. It says which one's synthesis. Is it synthesis? Yes or no? No? No. Okay, this has 2 reactants forming one product. That's yes, that's synthesis. So, reaction 3. Okay, 4. One thing breaking apart into 2 things. That's not synthesis. It's actually decomp. That's wrong. Here we have 1, 2, 2 things forming one product. This is also synthesis. And so we have our two answers, true, false. Synthesis, yes or no? Well, 3 and 5 are yeses. They are our answers. Okay, so this, easy to get thrown off by the crazy looking formulas. All you're looking at is just the general formula, right? Is it two things forming one thing? That's all you're looking at for synthesis. All right, 33. 5 more chemical equations. Look, it's the same ones. Okay, listed in the table below. And identify any decomposition. This is where your test-taking skills come into play. Look at this. Look at this. I already labeled them. Ooh, go right back to the one we were on. Look. Oh my gosh. Make sure they're exactly the same. Oh, they are. Which ones are decomp? Well, I labeled 1 as decomp, and I labeled 4 as decomp. I already did this work. I'm not going to do it again. Which ones are decomposition? I already told myself it was 1 and 4. Look at me go. I don't even have to spend any time on that sucker. Decomposition, one thing breaking apart into multiple things. Reaction 1 has that. Reaction 4 has that. And I already labeled it, and I'm going to use the work I already did, and I'm going to move on with my life. Question 34. Which statement correctly describes the similarity between liquids and gases? Okay, similarity. So, likeness, right? They're the same. Which one is the same between liquids and gases? Their shapes stay the same in any container. Okay, so if you pour liquid into a new container, so say you have a cup like this, and say you have a bowl like this, right? And if you pour in some liquid, that now has that shape, and then that will have that shape. Obviously, the shape did not stay the same. That's wrong. Their shapes change when they're in different containers. Well, yep, I just said that. Their volumes stay the same in any container. Okay, now for liquids, that's the case. The amount of liquid I have here is the same that I have here. Okay, you just pour it from one to the other, that's the case. But for gases, that's not the case. If you put gases in a bigger thing, remember they spread to fill their container. Okay, that's if you watch what's the Parks and Rec, there's a joke about that. Okay, the gases fill the container. Okay, so this is a similarity between liquids and gases. Liquids will stay the same volume, but gases will not, so therefore that is wrong. Okay, and then their volumes change. Well, this is the exact opposite of that. We know that one does, one doesn't, so that's wrong. So our first inclination of B was the correct inclination. Okay. Last full page. A scientist uses an instrument to observe the pattern of molecules in a substance. Now, this instrument, most likely, if you care, which you don't, is probably an electron microscope. Okay? That's pretty much the only thing that can see at that level. Pattern of molecules. The picture below shows this. Look, molecules. Before I even read the thing, let me look. They are in order. So they are ordered. Ordered. I can spell. Maybe. I don't know. They are in line. And there's not a lot of room to move. These are quick jots that I'm taking. Okay? What state of matter? Okay? Which state of matter is ordered? Which state of matter is in line with each other? Which one does not have a lot of movement? Well, solid. Okay? So you do your observations of what you are, and I guarantee you, once you do your observations, the question will become so much easier. If you skip straight to the question, you're going to have a lot of trouble with that. Okay? Well, not this one. This one's easy. But you'll have trouble. You'll have more thought process than necessary if you just do your thinking ahead of time. You trust your own brain. You don't trust... Listen, if you're going to the answers, looking for clues, remember, 3 of them are wrong. 3 of them are going to give you the wrong clues, and only 1 will give you the right clue. So that's a 75% chance of being wrong. You trust yourself, you're going to do a little bit better. Okay? Under the same conditions of pressure and temperature, a liquid differs from a gas because the molecules of the liquid... Now, this is asking what's the difference between liquid and gas. Now, in a liquid, they're grouped up, but they still have room to move past each other. In a gas, they're all spread out and moving all around. Okay, regular arrangement, neither of them have regular arrangement. That's a solid. Constant motion. Well, all of them are in constant motion. Solids vibrate, liquids move a little bit more, gases keep going, and plasma get going real quick. Okay? take the shape of the container they're in. We already thought to ourselves, you pour liquid into two different containers, it changes the shape. Therefore, the liquid takes the shape. You pour gas in different containers, it also takes the shape. Okay, so that's a similarity, and we're actually looking for differences, so that is wrong. Whereas the molecules are closer together. Okay, they're like a clump of molecules. Okay, not really ordered, just in a clump, kind of can move away from each other, can flow past each other. And then the gas, I don't know why I drew them so big, but they're much more and flying all around. Okay, so the stronger attraction keeps them closer together. That is our C. Cool. 37. Picture below shows solid floating in a liquid, so ice floating in water. Which of the following statements describes one way that solids are different than liquids? Okay, listen. Which of the following statements describes one way that solids are... Like, who cares? What is this for? Screw your picture. You're wasting my time. I don't care. What good is that picture doing for me? Nothing. The question has nothing to do with that picture. I don't know why they include... Like, why do people who write tests like that? Come on. They literally are giving you a picture to waste your time. That's the only reason that picture's there. Now, you could be like, well, you know, the liquid takes the shape of the container and the solid doesn't, and that's pretty obvious based on the thing. But you know that already. You don't need a picture for that. Come on. Don't waste your time. Which of the following statements describes the way solids are different than liquids? Okay, think to yourself. What's different about solids? They have a rigid structure. They're in order. They vibrate. They can't flow past each other. They have strong attraction because they're close together. They have low movement. Their molecules are very ordered. The liquid is not. It's more of a clump. Cool, let's go. Solids have weight and liquids do not. Come on. Everything has mass. Solids take up space. Everything, listen, mass has volume. It takes up space. You can't have mass without taking up space. What is this question? Solids have a definite shape and liquids do not. Okay, I apologize. I'm sorry for being so mad at you, Mr. Test Maker. I realize now that you wanted to show that the ice cubes keep their own shape and the liquid didn't, and you gave me this picture to do that, but I am smart and I don't need the picture. I don't need it. Solids have different volume, liquids do not. Okay, if you pour from a small glass into a large glass, you filled up the small glass, but you're not going to fill up the large glass because liquids also have definite volume. This is obviously definite shape. You don't need the no stinking picture to know the difference between solids and liquids. Don't waste your frickin' time. Question 38. The picture below shows a demonstration of water changing from liquid to gas as it boils in a beaker. Ooh, boiling water. Throw some ramen in there. Let's have a good time. Okay, don't forget the flavor packet. That flavor packet, they named it well. Which of the following statements explains why the demonstration cannot be used to prove that matter is conserved during the phase change? Okay, so what's happening to the matter? Okay, so it starts as a liquid, it then goes up as a gas. There is nothing here, so that gas is now dispersing into the room. If we were to take the mass of the beaker before and the mass of the after, we know that our mass would decrease because we lost some of the gas to the room. So water and the gas, the change of phase is taking place in an open system. We know our gas is leaving, and if it's in an open system, it's going to look like matter is not conserved because it's an open system. It's leaving. Okay? So we know that that is the case. Okay. Oh, also, B, water's changing both phase and temperature. Get out of here. If you still think that, and listen, remember our heating curves. We had our... Remember our heating curves, right? It went up. Then a phase change happened, then it went up, and then a phase change happened. This was our time, or energy. This was our energy added. This was our temp, right? as you went through a phase change, your temperature does not change. So water's changing both phase and temperature. Literally impossible. If you're changing phase, you cannot change temperature. Don't fall for the wrong answers. This is what I mean. If you're looking for the answers for clues, 3 of them are wrong. You're looking at the wrong place. The graph below compares 3 states of a substance. Physical state of substance and y-axis. Which of the following is the best label? Okay, that makes more sense. I was just laughing. I was like, someone forgot to label. All right, which is the best label for the y-axis? So we have our physical state here. As our physical state changes, what is changing with the y-axis? So let's go. Neutron density. So we're talking about neutrons now, eh? Neutron motion. So we are not talking about atoms and the motion of neutrons. Like, come on. Both of those are obviously not what we're talking about. So we're looking at molecules. So the density, remember mass over volume, and the motion, how fast they're moving. Okay? So as we look, we have solid, liquid, gas. Gas is higher, so we're looking at y-axis. You read y-axis from the bottom to the top. As you go up, you get more. So gas is more, would have more than liquid, which would have more than solid. Right? So gas is higher, liquid's in the middle, solid's at the bottom. So which one of these does gas have more of than solid? Molecular motion. Okay? Our gas particles are definitely moving more than our solid particles. So this one makes sense. As you change phases, you introduce more molecular motion. Solids are in place. Liquids are clumped up, can move across each other. Gas is all moving around far away from each other, and they definitely can move past each other. As we go up in phases, we get more molecular motion. And last but not least, number 40. When a sample of gas is cooled, it condenses into a liquid. Phase change, gas to liquid. In which of the following does the molecules... In which of the following ways do the molecules of the original gas sample compare with the molecules of the liquid? So again, gas versus liquid. Okay, what does it mean by neutron? It means neutrons in the nucleus, dude. We got protons and neutrons in the nucleus. We're not talking about nuclei here. We're not talking about protons and neutrons. Okay, we're talking about the molecules. Like, who cares about the neutrons? Get rid of it. Okay. Alright, so we're comparing our original gas to the liquid in question 40. The molecules are larger as a gas than they are as a liquid. Okay, so again, we have our solid, right? It's this nice ordered solid here. And then we have our liquid, which is not as ordered, still kind of clumpy. Okay, can kind of move across each other. Okay, and then we have our, well, why do I do that? I get so zealous. And then we have our gas, right? Our gas is moving all around. They are not close to each other. Okay, and they're moving. Okay, and then we have our plasma. And our plasma is moving super fast. We're going to draw arrows for how fast our plasma is moving. And then the kicker for plasma is charged. So we're going to put a plus here. We're going to put a plus here. Look at this. We're going to put a plus. They are charged. Okay, they have ionized, they have become ions, they are charged, they are going. That's plasma. So plasma, that's what our sun is, right? The stars are plasma. Our gas, liquid, and solid. Alright, the molecules are larger. Does your molecules change size? They better not. If they do, you're in trouble. Okay, so that's wrong. Molecules weigh less. Conservation of mass, guys. If you have the same mass as the solid as you do as the liquid, otherwise you're not conserving your mass. That's wrong. Molecules move faster as a gas than they do as a liquid. Molecules are closer together as a gas than they are as a liquid. Okay, so I drew them to all. Remember, gas is nowhere near as close as liquid, but they are farther apart. They have a higher temperature. Temperature is average kinetic energy. Okay, and then your average kinetic energy is speed. Okay, they're moving faster. That is the correct answer. Do you have to know much about plasma? Do you know that it's ionized gas and they're charged and moving faster than gas and more spread out? Then you're good to go. Okay, that's all you got to know about plasma. And we're done. That's our final question for the practice test. Now, I am finished. It's been a good hour and 50 minutes. If you have questions, throw them in chat now. Otherwise, we are going to call it a day, and we're all going to go to bed, and we're all going to wake up refreshed and ready to go, both on the science test and the other things that you have going on tomorrow. So if you have some last minute questions, go ahead and put them in chat. Otherwise, you should be done studying for the night. You should have studied before this, and then this should have wrapped everything up. And now you need to go to bed, get a good night's sleep, so you are mentally prepared tomorrow. For question 2, was it D? I don't know. Let's look. Question 2, yes, D. We had our reactants is equal to our products. Our products was 500. Our reactants was an unknown and 350. So we did 500 minus 350 to give us 150, which is D. That was number 2. I do not know, Deheezy. Alright, I'm going to call it there. At this point, you should be done with your studying for the night, and you should be going to bed, making sure you're going to sleep, getting a good night's rest, and coming in ready to go tomorrow. Have a good night. Hopefully you are prepared. Hopefully you didn't really learn anything because you knew all of it already. That's kind of the point where we need to be at. Okay, so go to bed, and we will see you tomorrow.